Welcome, everyone, and thanks for joining us today. My name is Bonnie, and I lead product marketing at Vespa. And today I'm joined by Zohar, who is our lead solution architect. This session is being recorded, and you will receive a copy of the recording within 48 hours after the session ends. Now, today we'll be digging in on how to solve one of the biggest challenges in e-commerce systems, delivering genuinely individualized experiences at scale without sacrificing latency. Now, for the structure of today's session, we'll start with a quick framing of the problem. Then we'll walk through the three things that you need to get right: your data model, your ranking logic, and your ability to act on signals in real time. And after that, we'll show you all of it in action in a live demo, and then close with some key takeaways before Q&A. Now, let's be precise about where existing systems break down, because the failure modes are architectural, not just operational. Most personalization systems fail shoppers in one of three ways, and usually all three at once. The first is stale data. Now, a lot of systems update shopper profiles on 24-hour batch cycles. That means if a shopper spends their lunch break browsing black heels, the system won't know about it until tomorrow, and by then the moment has passed. The second is one size fits all. Rather than treating each shopper as an individual, many systems group users into segments based on aggregate behavior. So people like you also bought is not personalization, it is demographic approximation. The third is fragmented systems. Signals exist: clicks, cart ads, removals, search queries, but they're scattered across separate platforms that never talk to each other. The search system doesn't know what the recommendation engine knows. The ranking layer doesn't know what the session tracking layer captured. You end up with personalization that's consistently wrong in ways that feel personal, which is arguably worse than no personalization at all. The result, as you can see in the illustration here, is a shopper that searches for green trousers may end up with results that are green cargo shorts or blue trousers or green shoes. So some of the characteristics apply, but not all of them. And this is the lived experience for millions of shoppers every day. So what does good look like? Well, we think about it in three principles. First, modeling all your data. Incomplete signals can lead to incomplete personalization. So you need to be able to capture the full picture: products, shoppers, and context in a single unified system. If you're missing any part of that, your personalization will struggle. Second, you want to rank, not just retrieve. A lot of search systems are built to find relevant items, but relevance isn't quite the same as personalization. You need a ranking layer that takes what you've retrieved and scores it specifically for this shopper in that moment based on their individual taste profile. And finally, you want to be able to leverage signals immediately. Shopper intent changes fast. Someone who opens an app looking for a gift for their mother is a completely different shopper than they were yesterday when they were browsing for themselves. Your system needs to capture those signals and act on them within the same session, not the next day. And these three principles are what Vespa is built around, and everything we walk through today maps back to one of them. Now, let me give you a concrete picture of what this pipeline looks like end to end, from a raw product image to a personalized result. First, it's about capturing product information, right? So we want to be able to write those product descriptions, and we use an AI vision model to read each product image, generate the natural language description automatically so that you have the rich, consistent product content at scale without requiring manual copywriting for every SKU. Then we extract the product attribute. So from that description, we're able to extract structured tags like color, material, style, fit, and these are each scored by confidence. So a product might come back with the color black as a 1, sleeveless as a 1, and silver as a 0.12. These attribute tags are what power personalization downstream. Once we have all of the product data, then it's about building that shopper profile based on interactions. So every interaction a shopper has, whether it's a click, an add to cart, or a removal, this updates their taste profile in real time. And importantly, recent behavior is weighted more heavily than older behavior. So what somebody did 10 minutes ago matters more than what they did last Tuesday. And then finally, we rank products instantly. So Vespa scores every product in the catalog against that shopper's live profile and then returns the most relevant results in milliseconds. So here's the key thing. All four of these steps run inside a single platform. There's no stitching together of separate services. And this is more than an engineering convenience. It's what makes real-time personalization actually achievable. So now I'll pass it on to Zohar to go a bit deeper on each of these building blocks, starting with the data model.
Thank you, Bonnie. So now let's look a little bit under the hood on how you would implement this in Vespa. Next slide. So with Vespa, a single Vespa document really captures everything a shopper cares about and everything the retrieval and ranking engines needs in one place. This includes structured attributes like the category, brand, title, price, stock, rating, reviews, and they're going to be used for filtering, faceting, and used as an input for the business rules. You also have a mix of lexical fields, title, description. Those will be leveraged for lexical retrieval and matching like BM25 and as input for embedding. One important point to notice are the actual tensors. So you have in this example, dense tensor, like for the text embedding, for example, to enable semantic search on the text. You have a dense tensor representing the image. This will enable search capabilities such as image to image or text to image, as you will see in the demo. And finally, you also notice at the bottom here, sparse tensor, like the product attributes, black, sleeveless, silver. Those are the ones that Bonnie just discussed about previously. And they offer a compact weighted representation of visual style attributes, which is a light way to do personalization by crossing those attributes against the user profile. This matters because Vespa data modeling really enables accurate retrieval and multiple search modalities. It contains every signal you can provide from a document perspective to rank in the most granular fashion, like lexical, semantic, visual, structured, behavioral with the user profile. All of this lives on the same document. It's served from the same node and is available and computed in real time in a single query. With Vespa, you can really model the product the way your business actually thinks about it. Vespa's data model is flexible enough to represent a product comprehensively. Text, embedding, image, embedding, sparse attribute, all living side by side with your normal structure field and available in real time for retrieval and ranking. Next slide. Let's double click a little bit on tensors. Most vector databases stop at a single dense vector board document. That's what you see in the top example on the right-hand side. And Vespa's tensor framework goes much further. A tensor with Vespa can be scalar, dense, a sparse map, or multi-vector structure. You see some of the example on the right-hand side here. What does it really enable? First of all, it enables you to represent complex data modalities. Tensors let you represent things a flat vector simply can't. Dense vectors for text, image, or multimodal embeddings for semantic similarity. Sparse map tensors for business rules, shopper preference, and attribute weights, like we discussed earlier. And a tensor can really be any generalized numerical structure. It can be a Colbert-style multi-vector that allows you late interaction models. And in addition to this, to offer you the ability to represent complex data modalities, You can also do tensor math. So we are here beyond similarity search that a vector database offers you. The tensor math happens at query time inside the engine where on the node where the data lives. And you can compose dot products, sum, joins, reduction to combine really multiple signal into a single relevant score. And this can be real-time signal. You can blend lexical signal, semantic, visual, and business signal into your own custom ranking expression. So you can really see you're beyond a simple, similarity search. There is no hop to a post-processing or to a second system to help with ranking. And in addition to tensor math, we offer you real-time ML inference on these tensors. So Vespa really runs ML models directly as part of the ranking. You can execute your own ONNX learn models such as GBTT, neural re-rankers at query time co-located with the data. You can feed real-time signals like the session behaviors, like we will see later in the demo, but other metrics such as the live inventory, where you can decay your ranking based on your inventory running low and being updated in real time as part of your documents. The result of this, you really get advanced ranking based on actual purchase propensity for the shopper, as well as your business rules that you would want to apply, like simply, expose less items where inventory run low, for example. So with Vespa, really, vectors let you do similarity search, and tensors let you build a ranking system with a very granular retrieval mechanism. Next slide. Okay, so how does this all come together? Why is the Vespa tensor engine a competitive advantage for e-commerce? First of all, like we discussed flexibility, right? You have one format for everything, for scalars, vector, matrices, maps. These are all tensors that are stored, queries, and used for ranking in real time. This could be product embedding, shopper preference, the live price being updated. You could have a dynamic pricing model, for example. The second is really the simplicity, right? Instead of having siloed system where you do the ranking in a separate system, with Vespa, you can express any business logic, like ranking formulas can express your business logic as tensor expression, right? This can be composable dot map, dot product, map, reduce, and join. Any ML model or business rules can be expressed without custom engineering or bespoke services. Those ranking expressions are quite intuitive. You can implement things like boosting high margin product or suppressing low stock items in very, very simple ways in a ranking expression. Another aspect of this is the speed, right? Because everything happens in the same system, you don't you rank in real time using this custom ranking expression, as well as you can invoke advanced machine learning ranking model in real time without having to hop to an external system, right? So Vespa will evaluate ONNX models and tensor expression at query time natively as close as where the data resides locally on the node. By just doing this, you really can eliminate a round trip that typically adds 20 to 100 milliseconds per query, right? Finally, this provides you a lot of agility in your time to market. You are able to ship all the AI features faster because data, models, and serving infrastructure are all live in one system, and new AI features and signal land as configuration changes. You don't need to hop infrastructure. You can add on the fly new ranking signals. You can do A/B testing in real time by diverging some traffic to test how your new strategies perform in terms of retrieval and ranking. You can swap those ranking model in real time when it comes time to put them in production. So really, Vespa offers you a flexible retrieval and ranking engine, which allows you to ship sophisticated, personalized products in weeks instead of quarters, all onto one system at production scale with predictable latency. Next slide. Now, let's take a look at the ranking engine. We just spoke about custom ranking expression, Tensor, math, ML models, real-time signal, and those gives you enormous flexibility. But expressive ranking and granular ranking in real time can be expensive. A question that we get often is, how do you stay fast at e-commerce scale without sacrificing accuracy? Our answer and Vespa secret sauce is multi-phase ranking. So instead of running the most expensive scoring on every candidate, Vespa filters and ranks progressively, spending compute only where it pays off, right? As a reminder, like we just discussed, the flexibility and expressiveness of Vespa ranking allows you to define custom ranking expression of your own that combines business logic with deep ML models, all in one place in one language. We offer you the ability to incorporate your real-time signal. This could be user behavior, business rules such as live inventory, directly into the ranking expression at query time. We provide you full control over relevance through composable tensor math. And that is across multiple data modalities, text, image, attributes, user profile. How does multi-phase ranking work in action in real life, right? The mechanism that keeps it fast is really to optimize retrieval by progressively refining result across multiple stages. So think of it as a funnel. You start with billions of products that you might have in your e-commerce store. Through going through the first phase ranking, you can reduce the candidate set to 1,000. By going through the second phase ranking, you can reduce that to hundreds. And finally, you could go through a third global phase optionally to isolate it to the final top-end candidates. And as you go through these multiple phases, you apply the most expensive models only to the most relevant candidates as you go through the funnel. And Vespa distributed computation scales accuracy without accurately without latency trade-offs. How does this work? With Vespa, we essentially intertwine retrieval and first phase ranking. So during first phase ranking and retrieval, we apply all your filters. We do the nearest neighbor search. And the phase one ranking should really be lightweight query time operators such as, BM25 and maybe a cheap vector similarity. The phase two ranking is your re-ranking, where a refined per node re-ranking can use maybe some ML models on a much smaller set. So candidates are reduced and we increase the complexity a little bit. Finally, the global phase happens on the stateless nodes, on the container node. Here, we can merge all the result across the content node and apply a final most expensive model. Like, for example, a propensity to buy re-ranker can be applied on your final candidate set coming out from all your models, allowing you to really retrieve the top K candidates where a user might actually convert into a purchase decision. So really, multi-phase ranking is how Vespa gives you machine learning powered accuracy without giving up on latency. You get the flexibility of custom expression, ML models, and the performance of a system built for billions of documents and thousands of queries per second with low latency within 150 milliseconds. Next slide. Now, let's discuss how all of this comes into action using our e-commerce use case, right? In the current example, what Vespa knows are the product data, like everything stored on the product document, like we just discussed. We know about the shopper profile, like we have a live taste tensor that we update as the user clicks through the web. You will see that in action during our demo. And the third item that Vespa has is the shopper's query, right? The shopper's query text, their session embedding, and any real-time signal sent at query time. The ranking engine is going to combine all of this. It's going to mix the keyword match, semantic similarity, personalization score into a single relevance signal. It's going to customize that by applying business rules that can boost or bury product. Like, for example, promote high margin product and bury the items where you have a high propensity to run out of stock, right? Every ranking decision is logged, so the team can see exactly why product A beats product B through ranking features. And finally, what comes out is your rank list, your top and most relevant and personalized product for these shoppers. The ranking explanation, like a full breakdown of what drove each product score. And all of this is done in a single round trip. Like all of the above happens inside Vespa in one single pass while we run the query. We didn't invoke any external re-ranker. We didn't have to invoke any ML inference services to help us with re-ranking. So in one query, one system, we had the product data, the shopper signals, and the search query. We are able to factor in and use as input parameters live signals such as the inventory level, some additional promotion that we want to consider in real time. And as the output, we get your top candidate set with a high propensity to buy, where you can convert your user browsing into a purchase. Next slide. Now let's see how all of this work in real time into a concrete example. Next slide. Okay, so how does this work, right? In terms of the user taste tensor that we have spoken quite a bit about during the presentation. What we see here is the shoppers, let's say, starts to view black heel shoes, right? So what happens as they click through this product, we essentially take all the tensors attribute from that product and start incrementing the different values of that tensors of representing the product attributes into the user profile. So let's say if they click on a single product and it has a value of 0.2 for black, 0.3 for formal, and 0.1 for heel, that's what we will start with. It's kind of weak signals, and they're added into the user profile. As the users navigates more and more and clicks on more items, we will keep doing the same. For existing attribute, we'll increment the value. For attributes that are not in there, remember, this is a very flexible model, we'll add new attribute key value pairs into the user profile, right? As the user go through, they might click on thumbs down, or there's a signal where you're reading that they do not like certain type of items. So instead of incrementing values, you can start decrementing them. So let's say the user has an explicit dislike for the color green. So we'll start giving negative scores or start decrementing from existing value on their taste profile. Now, as the users go through and start searching for more and more items, that user profile gets updated in real time, the taste profile, and we are using it in real time to rank and start surfacing the items that they're most likely to their taste as they browse through. And you will see all of it in action during the demo. Next slide. Okay, so without further ado, let's jump to the demo. For those who have been following our webinar series, this may look familiar to you. It's the Vespa demo shop, which demonstrates an e-commerce use case of fashion accessories and apparel. We've chosen this particular example because this domain really offers a lot of opportunity to demonstrate search accuracy as well as very granular personalization in real time. Um, so as we discussed during our presentation, the Vespa data model is very flexible and within same document allows you to represent many attributes, right? Like lexical attributes, structure attributes. In this case, we do have a sparse tensor as well, which represents the key attributes of the object. As a reminder, these were generated during the data engineering process when preparing the index file to ingest into Vespa. We've used an LLM to essentially extract the key characteristic of an item based on the image in a JSON key value pair that we're ingesting as a sparse tensor. How this comes into play is that we can, for example, use it for ranking for personalization use case, right? So let's say I have my user here and I can represent and model as a sparse tensor my user preference as well. So let's say my particular user has a preference for green items with a score of 5. These are all scores and ordinal values. They also love yellow items, but they don't have a liking for red items. So I'm going to give this one a negative score of 5. And let's save this. And as you can see now, is my user also has personalization features which are modeled as a similar sparse tensor. Now, if I go back to my main window, I can all of a sudden see that the feature product have changed. So what I can see here is that all these items are all of a sudden green and yellow due to the personalization, right? Now, when I click on a given item, I can see that in the recommendation on what I may also like, this has also been further customized into green and yellow object. The way this happens under the cover is we are essentially doing a dot product between two sparse tensor representation, one of the user preference and one of the items, and we are essentially surfacing first and ranking higher where we have some matches. And in this case, it's going to be on green and yellow items. Okay, now I want to take this opportunity to demonstrate you additional search capability that we've introduced in this product, in this round of the demo. So for example, let's say I'm looking for gold shoes. As you notice here, I do have the ability to do a text to image search. So let's say I'm looking for gold shoes and a text to image search. My search is a lot more accurate. What I see here is a bunch of items which are closer to my item description. These items are all gold shoes. The way this is done is I'm doing similarity search by embedding my query terms using the same embedding model that I've used to embed those images, and I'm essentially surfacing, the items that are that have the highest similarity. So I can get a lot more accuracy. The embedding model that I'm using is proprietary and comes from a Vespa partner. Another search capability I can demonstrate to you is image to image. So let's say I have a particular liking for a Donald Duck T-shirt that I somehow found on a video on social media, and this is the item that I'm actually looking for. So I can come in here and I can say, hey, I want to do an image search, and let's upload this image. And here we go. The first item that gets ranked is the same exact item that I was looking for. And I can also see very similar item, right? The same item in black, the same item with a different pattern, with a smaller Donald Duck. I can see all of this sweatshirt with the same cartoon character, as well as very similar into Mickey Mouse as well, right? So this is an image to image search, and the way it worked was pretty similar to text to image. What happened was when I uploaded the image, it got embedded using the same embedding model, and doing a cosine similarity search, I'm surfacing the items which have the highest similarity when comparing both images. Okay, so now let's look at another example, this time of dense personalization using the dense embedding. I demonstrated to you earlier how we can achieve personalization using sparse embedding, but this time let's take a look at what we can do using dense embedding. So let's say I'm interested in emerald earrings. Okay, so now I see a bunch of very nice emerald earrings of different kinds. And for example, let's click on this one. And as you can see in the you may like also, this list has also been personalized using the dense embedding. And each time I click, I'm actually refining further and further, the type of items that my user is particularly interested in, right? So when, for example, I click on this, I start to see very, very similar item with a mix of emerald, which has the same shape, the same tone, as well as a mix of diamond, right? So when it comes to jewelry, shoppers tend to have very, very particular preferences in terms of style. And this technique really allows us to show them items that are very, very close, and allows us to zero in into items that they may buy, right? Coming back here, I can start, let's say, liking certain items. So now let's change completely the style. And let's say I prefer more a dull color for an emerald. And I'm going to start liking, for example, this one. I may start liking this one, which are of a completely different style to what I demonstrated to you earlier. And I'm going to turn in the dense personalization. So as soon as I turn the dense personalization, I start to see that all the earrings that were very similar to what I liked are starting to show up here, right? So maybe I can further click on certain type of items. Let's say this one. And it's essentially gonna now show me items that are very similar to what I like. Okay, so how was this achieved? So let me go back to my user here and show you the profile. As you can notice here, you can see the personalization features based on the sparse tensor that I demonstrated earlier. But I now also have a dense personalization embedding. If I take a closer look, this seems to be 256 dimensions of float values. Again, as a reminder, this is using proprietary embedding models from one of the Vespa partners. And this dense embedding allows us to represent with a great degree of accuracy all the nuances of an items that a user liked, right? In terms of the exact shape, style of the earrings that the shopper was particularly interested in. How this was implemented is on the same principle as the personalization feature. Each time a user liked an item and click on an item, we implemented across all the different dimension of this embedding. We just incremented the different dimension value to bring us closer and closer and more, with a higher degree of accuracy to what the user is really looking for. So as you can see here, both of these features are valid. I would say the personalization feature based on a sparse embedding could be more costly. There's more room to error in terms of, subject to the LLM interpretation of the various attributes. It can be slower at scale. This approach is with the dense personalization. It's provides a lot more performance and accuracy. Um, it lacks a little bit flexibility, right? I cannot, provide some scores in order to force the personalization the same way I'm doing with dance personalization. Although dance personalization works super well when I want to rely on existing click item and start just incrementing based on that without, incrementing specific value. This demonstrates, the great flexibility that Vespa provides in terms of the transfer modeling and how this comes into play into accurate search and personalization. That's it. I hope you enjoyed this demo, and I'm going to hand it over back to Bonnie. Thank you.
So I hope you enjoyed that demo. Now we'll get into some key takeaways here. So the first key takeaway I would say is that generic personalization can cost you. So those stale batch signals and segment-based recommendations can decay relevance within a session. So this can impact click-through rates and average order value and cause shoppers to lose confidence in your platform. So the cost is real, even if it's hard to see in a dashboard. The second key takeaway here is really about tensors. So sparse tensors really make intent readable. So this is the architectural idea that we want you to leave with. So unlike dense embeddings, named feature dimensions like the color, style, are human readable, debuggable, and directly updatable. So you don't need to retrain a model to update a preference. You just update the value. The third is that real time is an architecture choice. So when you're able to do 100,000 writes per second per node, that means session signals like clicks, favorites, filters, removals, these reach the ranking layer in milliseconds. And this isn't a feature that you bolt on. This is really a decision that you make about how your system is built. And finally, one platform, not 5 services. So, having retrieval, machine learning, inference, personalization, and merchandising control all run in one platform. Inside Vespa, co-located with the index, really helps with performance and quality. So you don't have ETL pipelines, no separate scoring service, and no stitching systems together. And that simplicity isn't just operationally convenient, it is what makes real time possible. So that sums up our presentation for today. And we covered a lot of ground, and I hope it's given you a concrete picture of what modern real-time personalization can look like. So now we'll open it up for questions. Feel free, if you haven't already, drop some questions in there, and we'll get right to it. All right. So it looks like we have a couple of questions. And again, if you haven't If you haven't answered or asked a question yet, you can still drop that in. There is a Q&A portion at the bottom. So Zohar, I'll start with the first question, which is around the cold start problem. So how do you solve the cold start problem for new users?
Yeah, thanks, Pony. That's actually a very good question, which in e-commerce is a recurrent problem, right? Like when you don't know the user, it just comes in. How do you achieve personalization? I guess even with the approach that we are proposing, there's not really a good answer for that. Like when you start blank and you don't have any, if you don't know the user is not pre-registered and you haven't stored, his history, you can start with some default value, but in terms of what that user profiles look like. But I guess with the approach that we demonstrated here and that we discussed about, we can address the cold start problem really quickly. Like as the user starts browsing, literally, or whatever element that we got, anything on which he spent a little bit of time, we can start updating in real time the user tensor, and the cold start problem starts getting addressed really, really quickly versus doing this in batch mode and trying to guess that, right?
Mm, okay. Another question is sending my candidates to a re-ranker can happen in real time. So how does Vespa's real-time ranking approach differ?
This is actually an excellent question, right? What one might argue, I'm sending my candidate set to a re-ranker that's also considered real-time ranking. So how is the Vespa's approach different? So I would say the answer to that is architecturally what happens is with Vespa, first of all, a ranking is intertwined with retrieval, right? So it's not like we are finding a candidate set that I'm sending to a re-ranker post retrieval. That's the first aspect of real time. Secondly, ranking happens where the data lives and resides as close to the CPU as possible. So there is the low latency aspect of ranking. The fact that we can execute machine learning models like a propensity to buy, a learning to rank model directly during retrieval is another aspect of real time. Finally, the most important aspect is the signals, right? So for ranking in Vespa, you essentially have your own mathematical expression, and you can have three different input for ranking. One is the match features, like for example, what is the BM25 of the query terms versus the product, the title and description with different weight, right? So any kind of match features, those can go for lexical beyond just BM25, term proximity and whatnot. The second type of signal that we can use in real time is whatever you pass as a query parameter, right? So this can be input parameters to your custom ranking function. Like for example, personalization feature, like we demonstrated, the user profile can be passed in real time and appended onto the query so that we rank based on the user browsing history, right? And this is another aspect of real time. And finally, document features that we haven't really spoken about. So throughout the presentation, we spoke about, hey, you know what? You have the ability to decay and rank lower items that are getting low in inventory. So how do you really achieve that? Well, it's fairly easy with Vespa because Vespa is a real-time store and can support up to 100 of thousands of partial update per node per second. So you can literally maintain the real-time inventory or some other real-time attributes that represent the context of your products and your business rules, update them in a document, and then be able to compute your ranking in real time based on that.
Okay. I think we have time for one more question. You discussed modeling the product data, but how do you model the user side for personalization in Vespa?
Yeah, this is a recurrent question that we are getting, right? So I know that during the presentation, we just show you how you model your product, but we don't really talk about how you model the user. So in this demo, what we are doing is the user is stored in a separate collection within the same application. And with Vespa, you can query cross collection within the same application. And we essentially store, for this demo, it's very simple. We kind of have a registered user profile, and the user profile will have an ID. And pretty much the only thing we store is the sparse tensor representing the user personalization, right? So in essence, that's what you want to do. Obviously, in real life, it's more complicated. You need to have a session ID, some sort of an ID representing that user. And like we discussed, Vespa is a real-time store. You can update your collection when a new user session adds in. And as you browse through, you can perform partial updates on the tensor and increment, decrement in real time, or any other signal that you want to add to the user into that user profile. And you're able to use that as an input for your ranking and personalization.
Okay, awesome. Well, thank you for answering those questions. Looks like that is all the time we have for today. I do want to thank everyone who attended the session, and we will be sending that recording to you shortly after the session ends. So thank you so much and have a great day.